Hey everybody, this is Mr. Beckstrom, and I'm going to go over a question from section 4.5 in the homework. It says a rectangular flower garden with an area of 190 meters squared is surrounded by a grass border 1 meter wide on two sides and 2 meters wide on the other side, or the other two sides are shown in the figure here. What dimensions of the garden minimize the combined area of the garden and the borders? All right, so the first thing we want to do is just kind of label what we have. And so we know that the area of the flower garden is equal to 190, and you can put the meters squared there if you want, although it's not really important to put the units when we're working this out. And we want to minimize the combined area of this and the surrounding area here. So let's go ahead and label our garden here because we need to know the dimensions, or we need to at least kind of label the dimensions here. So let's call the bottom width and the vertical distance height. That's usually what we do with a rectangle here. And this is for the flower garden. So our objective function here is the area, and since we're talking about two different areas, I'm going to put a little subscript here, C, that shows that this is the combined area, is equal to. Alright, so what is the combined area, width and height? And remember, the combined area is going to be the width times the height of this larger rectangle here. So it's going to be, the width is going to be the width of the smaller one plus 2 here and plus 2 there. So it's going to be width plus 4. And this is basically the width of our combined triangle. And it's going to be times the height times the height of our combined triangle. And that's going to be h plus 1 plus 1. So h plus 2, h plus 2. So this objective function shows us what the area, because that's what it's asking us to minimize or maximize, the area of the combined, or the combined area of the garden and its borders. Now, could you have taken the W to be this length here and the height to be this here for your objective function? Sure. If we had done that, then our combined area here would have just been width times height, but then we would have had to do a lot more substitutions and subtractions in there in order to get it down to one variable. And that's the key here. The key is we want this objective function here just down to one independent variable, and here we have two. So this is where the constraint functions come into play. So we look to see what additional information they gave us. So they gave us that the area of the smaller, so I'm going to put a little f here, of the flower garden is equal to 190. Now remember what area is. Area is length or width times height in this case. So width times height, and it makes it a lot easier because we notated the smaller one as that. If we had notated the larger rectangle as width and height, then the width and the height, we would have had to have subtracted 4 from the width and 2 from the height in order to set up this function here. And like I said, it just would have been a little bit trickier of substitution, but we could have done it that way. But width times height here is equal to 190. And the idea is that we're trying to substitute something over here so we can get into either widths or heights. It really doesn't matter which one we do. So in this case, I'm going to solve for width, and that's going to be 190 over our height. So that's what the width is equal to. So we'll go over here and make that substitution. So width is equal to 190 over height plus 4, and this is going to be times the height plus 2. So here is our objective function right here. And now let's go ahead and FOIL this out. So the first two terms multiplied by each other, the h's will cancel out. I'm just left with 190. The inner terms is going to be plus 4h. The outer terms, that's it's going to be 380 over h. So plus 380 over h. And the last terms will be plus 8. So the two constants will combine to make 4h plus 380 over h plus 8. Alright, so this is our objective function cleaned up, and this is what we want to minimize. So remember that the local mins and the local maxes exist at the critical values of our function, and we find the critical values by taking the derivative of the function and then setting it equal to 0, right? Or where the function is undefined. But the only place that this function here, well, let's find where the derivative will be undefined at. So in order to take the derivative here, we're going to use I'll use the power rule. So this is just going to be 4. And then let's do this one off to the side here. So I'm going to find the derivative of 380 over h. I could use the quotient rule, but it's a lot easier just to bring the h up to the top. So 380 times h to the minus 1. You can just bring that h up here, and then you just really apply the power rule. So this is going to be the derivative with respect to x, or excuse me, with respect to h, is going to be negative 380 h to the negative 2, and that's just equal to negative 380 all over h squared. So this is minus 380 all over h squared. So this is the derivative of our objective function. So we're looking for where this is either undefined or equal to 0. I always start with undefined. So the only place this is going to be undefined is where we get a 0 in the denominator here. And we're not looking for a height of 0 because we need a positive height. So that means that we really only care about where this thing is equal to 0. And let's talk about the constraints real quick. The only constraints that we have for this is that the width and the height are going to be over 0, right? Because if we have a height or a width that's equal to 0, then there's no possible way that the area can equal 190. So the constraint is both of these are above the 0. All right. So let me give myself a little bit more room. So what we're going to do is we're going to set this equal to 0 then. So 4 minus 380 over h squared is equal to 0. Multiply everything by h squared. I'm going to get horrible 4. I'm going to get 4h squared minus 380 is still equal to 0. Add 380 to both sides and then divide by 4, and we get h squared is equal to 95. Therefore, h is equal to the square root of 95. The square root of 95. So our optimal height here is going to be the square root of 95, and to find the width, we just plug it right back into that constraint equation that they gave us, so where width times height is equal to 190. So substitute that height in there. So width times the square root of 95 is equal to 190. And kind of go back up here. So the width is equal to 190 over square root of 95. and rationalizing the denominator by multiplying the top and the bottom by square root of 95, I'm going to end up getting 2 times the square root of 95. So that will be my optimal width of that. All right, guys. I know this is a lot of work, but it's really about starting off, finding your objective function here by seeing what they're asking you to minimize or maximize, and then just kind of cleaning that up, and then taking the derivative or getting that into one variable, and then taking the derivative, setting the derivative equal to 0, and find out where it's undefined, and solve for it that way. All right, if you have any questions, let me know, and I hope you all have a great rest of your week. Thanks.